Capacitors. A capacitor is a device that stores energy in an electrostatic field. A capacitor is a very useful device in an electrical circuit that allows us to store charge and electrical energy in a controllable way. In circuits, capacitors are often used to smooth out sudden variations in the line voltage that can damage computer memories, etc. So some applications of capacitors are given here. For example, they are used in radio tuner circuits, variable blocks, DC voltages in AC circuits. They act as switches in computer circuits. They trigger flash bulbs in cameras. They convert AC to DC in a filter circuit. They are used in RAM chips. They are used in oscilloscopes. They are in many more places. So how do we make a capacitor? A capacitor is a very simple device, physically, when you think about it. So two conductors that are isolated from each other and from their surrounding form a capacitor. When a capacitor is charged, the conductors carry equal but opposite charges of equal magnitudes. Two conductors are called plates, no matter what their shape looks like. And a simple capacitor consists of two parallel conducting plates of area A separated by a thin gap, air or some dielectric or some other material. If a charge Q is placed on one plate, Q minus on the other, the potential difference between them is going to be V. Then the capacitance of a capacitor is defined as Q over V. The SI unit, C, which is for coulombs divided by volts, is called a farad, named after the famous scientist Michael Faraday from the early 18th century. So the magnitude Q of the charge on each plate of a capacitor is directly proportional to the magnitude V of the potential difference between the plates. C equals Q over V. C is the capacitance. The SI unit of capacitance is the farad, but in general we use terms microfarad, millifarad, or picofarad, given here. So the different types of capacitors that are used in general are parallel plate, spherical, and cylindrical capacitors given here. So parallel plate capacitors are two plates separated by a distance. Spherical are two spheres together. Cylindrical are two cylinders together separated by either a material that's placed inside it or they are separated by air. Capacitors in series and in parallel. Capacitors can be wired together in two ways. They can either be wired parallel to each other or they can be wired in series with each other. Capacitors in circuits connected by wires, such as the positive plates are all connected together and all the negative plates are connected together, are called parallel circuits. So the equivalent capacitance for a parallel circuit is going to be C1 plus C2 plus C3. For a series, the capacitors are wired such that positive plate of one capacitor is connected to the negative plate of the next capacitor, and so on. In this case, the equivalent capacitance is given by 1 over C1 plus 1 over C2 plus 1 over C3. Energy stored in an electric field. Any charge configuration has a certain electrical potential energy U equal to the work, which may be positive or negative, that is done by an external agent that assembles the charge configurations from its individual components, originally assumed to be infinitely apart and at rest. Potential energy is similar to that of mechanical systems, such as a compressed spring or an Earth-Moon system. This work is stored as potential energy U in the capacitor, so that the potential energy U will be equals to Q squared over 2C. Q, which is the charge, is given by C delta V, or U equals 1/2 C delta V squared. Another very important concept is called energy density. Potential energy per unit volume between parallel plate capacitors is given by 1/2 epsilon naught A E squared. A parallel plate capacitor looks like this. So it will have a positive charge and a negative charge and an electrical field inside it. This is our very simple form of what a capacitor plates look like. However, in real life, the ideal parallel plate capacitor from last slide does not actually look that way. What we do have is something that is shown in the picture here, where on the fringes you have fringing fields which are called fringe fields, and they take away from the ideal situation of a capacitor. In general, I want to make this point very, very clear. These fringe effects are very, very tiny as compared to the size of a capacitor. So we, in general, neglect these fringing fields. And we are going to always assume that our capacitor is ideal and it has an absolutely uniform electric field. So now let's look at an example. In one kind of computer keyboard, each key is attached to a plate of parallel plate capacitors, and the other plate is fixed in position. A capacitor is maintained at a constant potential difference of 5 volts by an external agent. When the key is pressed down, the top plate moves closer to the bottom plate, changing the capacitance and causing charge to flow into the circuit. If each plate is a square side of 6 millimeters and the plate separation changes from 4 millimeters to 1.2 millimeters when a key is pressed, how much charge flows into the circuit? Does the charge on the capacitor increase or decrease? And assumption is that there is no air between the plates that there is air between the plates instead of a flexible insulator. So in this problem, what we are given is that the key is here and that it is connected to a base, which is here. And it says that the flexible insulator, the movable metal plate, when you press it down, this is where the movable plate is, and this is where the fixed plate is, right? So as you press the key downwards, so this is my key, as you press it downwards, this is able to move up and down. So what it says is that the capacitor is held at a potential difference, delta V, of 5 volts. And the plate square side, so the plate is 6 millimeters or 0.006 meters. And it says that its separation, which is D, can go from 4 millimeters to 1.2 millimeters. Okay? When the key is pressed. It says how much charge flows through the circuit. So part A is we have to calculate Q. How much charge is flowing through the system? So we know delta Q, which is what we need, is equals to QF minus QI. So the total charge that flows through the system is QF minus QI, which means that I need to find, I know Q is equals to C delta V. So this will be CF delta V minus CI delta V. Now what do I know about C? C, I know for a parallel plate capacitor will be given by A over 4 pi KD. Okay, so I can plug this in here and in here. So I get A over 4 pi KDF minus A over 4 pi KDI, given that delta V is the same, which is the potential difference that it is held to. Okay? Now, in this case, A of the plate does not change, so I can take A common out, divided by 4 pi4 pi K, and delta V out. So what do I get? 1 over dF minus 1 over DI. Now, what is DF? DF is the final at which it can go to, and DI is the initial, which is what it was. Once I plug in the values, oh, by the way, what is A? A is the area, right? Area of the sphere, area of the plate. So this means that if this is a plate which is 6 millimeters wide, so how will I find the area? Area will be length times width, which is 0.006 times 0.006. So all we have to do is calculate that, and that will give me the answer in meter squared. Delta V is given, which is here. A I can calculate, K I know, DF and DI I know from here and here. All I need to do is plug in the values, and once you've plugged in the values, you get delta Q equals plus 0.93 picocoulomb. Now let's talk a little bit about energy stored in a capacitor. So fibrillation is a chaotic pattern of the heart activity that is ineffective at pumping blood and therefore life-threatening. A device known as defib is used to shock the heart back into a normal beat. The defibrillator discharges a capacitor through paddles on the skin, so some of the charge flows through the heart. If an 11 microfarad capacitor is charged to 6 kilowatts and then discharged through the paddles into the patient's body, how much energy is stored in the capacitor? How much charge flows through the patient's body if the capacitor discharges completely? So, in this case, it is asking us in part A that an 11 microfarad capacitor that is charged to 6 kilowatts, so delta V is 6 kilowatts, and then it is discharged through the paddles. How much energy is stored? So I need to find the stored energy. And the formula for stored energy is 1/2 C delta V squared. Sorry, that looks like a U. No, it's not a U, it's a delta V. So it gives us 1/2 C is 11 microfarads, and delta V is 6 kilowatts squared. Remember, this is 10 to the 3, and this is 10 to the minus 6. So once you calculate it, it comes up to 198 joules of energy was stored in the paddles. Part B, it asks us how much charge flows through the patient's body if the capacitor discharges completely. So the formula for that one is Q equals C delta V, right? Which means this is going to be 11 microfarad times 6 kilowatts. Again, do the conversion, and it's going to be 0.66 C.